Hi there. My name is Jimmy Angelakos, and my talk is titled Listen Carefully, How Notify Can Trip Up Your Database. And it is a real world story. It's a thing that happened in production once upon a time, and it's a real pitfall and situation that can be caused when using this mechanism in Postgres. So I think it's really useful to talk about it and show you what it can cause and also how it can be fixed. So let's get started. Listen carefully how notify can trip up your database. And we'll see exactly what this cryptic sentence means during the talk. So I'm Jimmy Angelakos. I work at PG Edge. I'm based in Edinburgh in Scotland. I've been involved in the open source community for over 25 years, and I'm honored to be named a Postgres significant contributor to the project. I'm a member of the Postgres Europe Diversity Committee, and I've written a couple of books, PostgreSQL Mistakes and How to Avoid Them, and I've co-written the Postgres 16 Administration Cookbook. I've also created a Postgres extension for the visualization and time series analysis of Postgres internal statistics called PGStatViz. So let's see what this talk is about. Listen Notify is a feature that is really elegant, it's powerful, and it also has a trap. So because this is a real world story that happened in the wild, we'll see how we stepped in that trap, how we found out that we had stepped in it, and also how we fixed it. So let's see what listen notify is about in Postgres. The use case for these two commands, listen and notify, is to send asynchronous notifications. And usually that's useful in conjunction with an application that acts as the client to your database. So what is exactly the use case? It's letting parts of the application communicate with each other and with the database. So it's what we call inter-process communication, or IPC. What's great about this mechanism, listen notify, is that it's built into Postgres. It's really lightweight, and it requires zero extra infrastructure, which for a fan of the KISS philosophy, such as myself, is amazing because you don't need to depend on external things such as Redis, Kafka, RabbitMQ, all these other message buses or data buses. You just need to use SQL. So it sounds really awesome. So let's see, how does it work? So internally, it's simple inter-process communication. Postgres, after all, is a multi-process system, and the pattern for listen notify is publisher and subscriber. So you just do it the other way around. You start listening as the subscriber, and then you send the notifications as the publisher. It can send messages or payloads that are up to 8 kilobytes, 8,000 bytes actually. This is configurable at compile time. So it's not a hard limit. You can make Postgres send bigger payloads if you roll your own. And additionally, it's transaction safe. This is a mechanism that is transaction aware. So the notifications for your transaction are delivered if the transaction commits. And this is what makes it really safe. Because if you want to notify a third party, such as your application, that something happened in the database definitively, that it was committed in the database, then you send a notification. If that action has indeed succeeded and the transaction is committed, then the notification gets sent. So that's a lot of theory. Let's see how exactly we can do it. So how you use it is there is session A, let's say, that is listening on a channel. So it's announcing that I'm now subscribing to this channel. So listen, order was watchers JSON is my example. So now session A is listening on the channel that's called order watchers JSON. Session B is the publisher in this case. So it's saying, tell this channel that something happened. So it's running notify order watchers JSON, the channel, and then a payload, which in this case is a JSON payload as a string, which is order ID 42 and status is completed, which is what the listener is waiting for. The payload is the information that they want to get notified about asynchronously. And session A indeed receives from this channel order watchers JSON, the payload, and that is 100% it. That's exactly how it works, and it's as simple as that. Now, let us see what happens when you put this in production. So this production setup that we're going to be talking about is a Postgres trigger that contains the notify, and then that notification goes to a legacy application, and that legacy application then puts the message on Redis, and because that's where the newer components of the system are. So the newer components are connected to Redis. The legacy app is also connected to Redis. The legacy app has the database, and therefore when something happens to the database, the legacy app is notified, and it also can tell Redis, so the newer parts of the system can know about this notification, this event. And notify, exactly what it does is it tells the legacy application that a transaction was committed. Now, it is worth mentioning that since this system was put in place, there was a significant increase in customer traffic. So we'll see why that is important. Because with the increase in customer traffic, people started noticing a few symptoms. One day, the worst of the symptoms was there was a sudden spike in canceling statement due to lock timeout log lines. So in the logs, they would see things like this, which were quite unusual to see. So this signified that there was a lock cascade and that the transactions were stalling at commit time. The consequence of that is that errors started appearing on database servers that were really busy. And because things were erroring out or delaying, the client requests had increased wait times, which we can see in the monitoring. So it was really necessary that something was done about this. We needed to investigate why this was happening because the environments that we had with high transaction volume on the system were starting to suffer from this. So pull the logs. What did the logs show? The logs showed things like process this acquired access exclusive lock on object 0 of class pub62 of database 0 after 1100 milliseconds. And then another log line and another and another. So they looked exactly like this, the errors that we saw in the log. So the processes were waiting over 1.1 seconds at that point just to obtain a lock. But what is that lock? What is object 0 of class FOB62 of database 0. It obviously was not a row lock, and it wasn't a table lock. So we found out that class 1262 was the PG database system catalog. What? Why was something attempting to lock the global database catalog for every single transaction? So this is where the trap was, and the trap is serialization. What do we mean? So to guarantee the ordering of these notifications, every single commit that had a notify call pending required to obtain an access exclusive lock on this global object. And what is another way to say guaranteeing the order of something? It's serialization. So what are the implications here? The implications are that because we were putting notify inside of our trigger, this means that we were forcing transactions that were in reality concurrent to queue one behind another because the order of the notify calls needed to be guaranteed as commit order. So we effectively invented accidental serialization, something that should be concurrent and parallel was actually happening one thing at a time. The mistake was that whoever wrote that code initially treated listen and notify as a concurrent message bus, where in reality it wasn't, because Postgres treats listen notify like a globally serialized queue of notifications. And when you're trying to parallelize and do concurrent stuff, that is not the way to do it, because every transaction commit triggered a notification. So as we were seeing more and more customers committing transactions, we had more commits as a volume of commits that were competing for the same global lock. This means that we were artificially restricting our throughput. And as we saw, errors started appearing because the database started killing transactions that waited for too long to obtain this lock because of the lock timeout settings on the production server. So how do you fix something like that? We started exploring solutions. Our first instinct was to just fix it in the application. The problem was that the application, as I said, was a legacy app, and nobody wanted to take the risk of changing something that had been stable and immobile for years. Basically, nobody wanted to touch the legacy application. Don't touch it because it will break. It's a classic development pattern that we see out in the field. And secondly, the solution would have been too complicated because we would have had to create some asynchronous process that was listening for these things asynchronously and not blocking the database and so on. So it turns out that wasn't the right solution, our first instinct. So then we started thinking, can we solve this from the databases side so that we can avoid touching the application? So the problem we're trying to solve is that the notification sending is coupled to the transaction committing. And this is what we need to tackle. So how did I solve this entirely from the database side? First of all, we changed the triggers. Instead of sending a notification, the triggers would write that notification into a notification queue table. This means that they didn't need to obtain any global lock because the trigger was just writing to a separate table. Secondly, the notify function that was sending the notifications needed to grab what we call an advisory lock to ensure that there is only one sender at a time. Remember, we don't want contention on this global notify lock on the database table, on the database catalog. So the third thing is after you have obtained this lock within this trigger function, you send the notifications that have queued up to that point. And let's see what this means. That the decoupled notification operation is now asynchronous because transactions are unblocked immediately. If they cannot obtain the lock to send the notification, then they're not waiting on it. They're giving up on it immediately. The notification is queued in the table. It remains for the next transaction to pick it up. So what does this notification queue table look like? It was an unlocked table. Why? Because the storage of notifications is ephemeral, right? We don't need it to be crash safe. It's something that needs to notify systems in near real time. So the storage there is temporary, but a temp table isn't good enough. We want an unlocked table because we don't want the churn within this table to affect the write-ahead log. So this doesn't create any bloat because unlocked tables don't go through the wall. So the table looked like order.notification queue. It's a timestamp. The default, because we didn't need to set it explicitly, we set it to be the clock timestamp of the server at that moment in time. And the payload is just text. Now, the changes that we made to the trigger. So by queuing, it means that we no longer call PG notify directly, but instead we insert this JSON payload into the queue. And the trigger function now contains payload, JSON build object, whatever this is a simplified version of the real world thing that we were sending. Then it checks. If payload is not null, then insert into the notification queue the payload. And it's as simple as that. Now, the next step in the trigger is updating it to do the advisory lock stuff. So after having queued the notification, we attempt to obtain an advisory lock. And this advisory lock only needs to be transaction level. It doesn't need to be global across the system. And it is non-blocking for the rest of the operations. That's why it's called an advisory lock. It's something we want to control. So it tries to do lock acquired equals PG try advisory transaction lock. It obtains an advisory transaction lock for the lock ID that we've hard-coded. And then it checks. If we have indeed obtained this lock, then send the notifications. Otherwise, do nothing and just commit as normal. So we found out the cutoff. We generally don't want to send notifications that are older than 10 seconds. Of course, there's no point. We need this to be almost real time. And so continuing on from that point in the function, we see that we're looping over the notification queue while deleting. And I love this Postgres feature. You can say delete from the table where tstamp is less than 10 seconds, returning star. And this star feeds into the next select, which is select n payload tstamp from notification from notifs n, where n timestamp is greater than the cutoff. So only newer notifications ordered by timestamp. Now we have fetched the notifications from the notification queue table, and we just loop over them and send them in a batch. So we perform now that we have the lock and we know that there's no one else who can obtain this advisory lock and try to send notifications at the same time. We do a perform PG notify to our channel, the payload, and that's the entirety of the loop. These are the relevant parts of the function. The logic, the business logic is not relevant in this case. So how does this fix work? In practice, the transactions that fail to obtain the lock instantaneously, they simply commit. The queued notifications are picked up by the a transaction in the future that managed to get the lock. This means that PG notify, as a consequence, was not contented because there's only one sender at any moment in time. So there's only one short lock held for PG notify for the entire batch. How did we test this? And you should test everything and trust nothing, including your own code. We tested this for correctness, concurrency. We tested for race conditions that could arise because we changed the queuing logic of the whole application / database interaction. We tested it for performance, regressions in case it broke something, on a clone of the production database that had a synchronous standby. Why? We needed a synchronous standby because that's what production had, to introduce a realistic commit latency, because commits don't happen instantly when you have a synchronous standby. You need to do the round trip to make sure that it has been committed somewhere else. And then we stress tested 4 times the transaction volume that we were seeing in production at that moment in time, which is great because we got great results. We sustained the rate of 4 times the production volume on a database instance that was actually smaller than production. So that's a good thing. But because I said trust nothing, we also had logging. So right after the insert statement, I put in a little thing that would report the queue length in the database logs just so that we could keep an eye on it. So this code reports the queue length in about 0.5% of all transactions for logging purposes. I chose the modulo of 199 because 199 is a prime number, so it's unlikely that we would end up in a bad pattern of exactly 100, 200 batch and so on. So if the current transaction modulo 199, then we just set the logger verbosity to, because we just want to output this single line that raises a warning that says order notification queue length. And then in order to avoid selecting from the notification queue table, we would just do a pgstat get live tuples for that table, which reports almost exactly the size of this table. And then we need to exit the state of logger verbosity. We would just reset it. The results that we got was we saw an immediate difference. The lock timeout errors disappeared in production, and in our stress tests, we had transactions throughput that more than tripled compared to the old code. So now the performance was again bound by the hardware instead of our self-induced bottlenecks that our code had. So the client requests saw reduced wait times, and that's a good thing. So to recap all of this, Listen Notify is a powerful and elegant feature that Postgres includes. However, it can become a silent bottleneck when you have high concurrency and high throughput systems. So watch out for these kinds of things, global locks, especially if they are in a high frequency trigger that gets triggered hundreds of times a second. Advisory locks are awesome. You can use them for manual concurrency control, which is what we did here. We didn't want two callers to send notifications concurrently, and we fixed that. The bottom line is you should keep Notify out of your hot path in whatever your application happens to be. So thank you very much for listening. This is a topic close to my heart, mistakes you can make with Postgres, and that's why I wrote the book. You can get a discount with this code on the book or any other product on manning.com. And I will now join the Discord to answer any of your questions. Thank you so much for listening.